In this video, we're going to continue the discussion of scattering of an electromagnetic wave by an oblique angle. Which essentially means scattering at some any angle you choose, some angle of incidence. So if we have some interface between medium 1 and medium 2, then I can define my wave coming in at some angle of incidence. And what we found in the previous lecture was that you can relate the amplitudes. So the amplitude of the reflected wave was this coefficient alpha minus beta, alpha plus beta, and that's the amplitude of the incident wave. And then the transmitted wave amplitude is 2 alpha plus beta times the amplitude of the incident wave. Okay, so what I wanted to discuss now is a special case where alpha is equal to beta. So this is going to give us what's called the Brewster's angle. Okay, so what is alpha and beta? Alpha is the cosine of the transmitted angle divided by the cosine of the incident angle. And beta is mu 1 n1, I'm sorry, n2, the index of refraction, divided by mu 2 n1. Okay, so what we're going to find is that, or what we want to calculate is when we set alpha equal to beta. What is the result of that? Well, if alpha is equal to beta, according to this equation right here, that means that the amplitude of the reflected wave is 0. So you get no reflection at all. So we pick an angle such that we're not going to get any reflection. We're going to get 100% transmission. So here's my incident wave. I get no reflection. I only get 100% transmission. Okay, so let's set those equal to each other. So I said alpha was cosine theta t over cosine theta I. So I can rewrite this as the square root of 1 minus sine squared of theta t over cosine theta I. And actually, why don't I change those subscripts, since to, instead of saying the incident angle, I'll call it the Brewster's angle, theta b. So theta I now becomes theta b. So it's a change a variable. Okay, so this now is, well, I'm sorry. I'm getting ahead of myself. That is still theta t. And from Snell's law, we know that sine theta t is n1 over n2 sine theta incident, or b. Okay, so now I can get to the equation square root 1 minus n1 over n2 sine theta b quantity squared over cosine theta b. And all of that, I said, is going to be equal to beta. Okay, so let's rearrange this. If I square both sides, multiply by the cosine, I get 1 minus n1 over n2 quantity squared sine squared theta b. is equal to beta squared cosine squared theta b. And then I try and rearrange it a little further. The cosine squared I can write as the sine squared. So I have 1 minus n1 over n2 quantity squared sine squared theta b is equal to beta squared 1 minus the sine squared theta b. Okay, so now I get 1 minus beta squared is equal to n1 over n2 quantity squared minus beta squared times the sine squared of theta b. So if I rearrange this now to solve for the angle, which is what I want to do, I get sine squared theta b is 1 minus beta squared over n1 over n2 quantity squared minus beta squared. Okay. So now we're going to assume that both materials, 1 and 2, have the same magnetic properties. So the permeability of 1 is the same as the permeability of material 2. So that means that beta now is just going to be n2 over n1. So then that reduces to sine squared Brewster's angle is equal to 1 minus n2 over n1 quantity squared over n1 over n2 squared minus n2 over n1 quantity squared. A lot of n's in the equation. Okay, so it probably would have been better if I had left things in terms of betas. So that would have been sine squared theta b is 1 minus beta squared over 1 over beta squared minus beta squared, which then I can rearrange, multiply both sides, both top and the bottom, by beta squared. So I get beta squared times 1 minus beta squared over 1 minus beta to the 4th power, which I can factor. So that's beta squared 1 minus beta squared over 1 minus beta squared 1 plus beta squared. Now things are starting to look good. So I can cancel 1 minus beta squared on top and the bottom, and I get beta squared over 1 plus beta squared. Okay, so that's looking pretty good. If I take a look at this, then what do I get? So let me rewrite this. Sine squared the Brewster angle is equal to beta squared over 1 plus beta squared. And, okay, so if you work that out, what do you get? You get, in the end, that the tangent of the Brewster angle is equal to n2 over n1, which is essentially beta. Yeah. So I'm not going to go through the algebra, but what you find is this result, that the tangent of the Brewster angle is equal to n2 over n1, which is basically beta. Like so. So if you now consider the intensities, the intensity of the incident wave, so I sub I, is 1/2 epsilon 1, the speed v1, the amplitude of the electric field squared, times the cosine of the angle. Because we basically have the pointing vector dotted into the z direction. So that's why we have the cosine of the angle in there. Okay, so the reflected amplitude, the reflected intensity is 1/2 epsilon 1 v1, the reflected amplitude squared, times the cosine of the angle. And the same thing for the transmitted, except for now it's material 2 with the speed of the wave v2 like so. So this reflection coefficient R is just the ratio of the intensities, which in this case everything cancels. The angle is the same, permeativity is the same, and what you get is just the ratio of the amplitude squared, which in this case would be alpha minus beta over alpha plus beta quantity squared. And the transmission coefficient is the ratio of those intensities, which in this case the 1/2's cancel, but you can't cancel out the permeativities. You can't cancel out the speeds. And you get the ratio of the amplitudes squared. And then you get the ratio of the cosines. So that's the transmitted angle, and that's the incident angle. Well, the ratio of those cosines is our factor alpha. This part here turns out to be beta. I said the ratio of the cosines is alpha. So what we get for the transmission coefficient is alpha beta times the ratio of the amplitudes, quantity squared. Now that we said is 2 over alpha plus beta squared. Okay, so what you get is 4 alpha beta over a alpha plus beta quantity squared. So this is the formula for the transmission coefficient. This is the formula for the reflection coefficient. Now this is for any angle, so I kind of didn't really specify when I was talking over the result of the Brewster angle, but so after talking about the Brewster angle, I switched to talk about just looking at the general formula for the intensities, and what you get is reflection and transmission coefficients. And so if you were to add them together, what you would find is that the sum of those two are equal to 1, because energy has to be conserved. So you can work out the algebra to prove that is so. It's not that hard. If I now want to apply this to the Brewster's angle, where alpha is equal to beta, then the reflection coefficient is 0, and the transmission coefficient is alpha times beta, which is just beta squared, over times 4 over 2 times beta squared, because alpha is equal to beta. That is equal to 1. 100% transmission,